This is the SHIMET course on the Advanced Baseline Imager, the ABI, one of two instruments on GOES-R that measures the Earth's atmosphere. This course has been created with funding from the GOES-R program, and it will help you understand imagery from the ABI. Contributors to this training are listed on this slide. This module, developed by Scott Bachmeier, focuses on weighting functions for the water vapor channels. I'm Scott Lindstrom. Weighting functions show the depth of the atmospheric layer, as well as the peak altitude, from which radiation being sensed by a particular infrared spectral band is originating. The figure on the right shows plots of weighting functions for the 10 ABI infrared bands on GOES 16. The plot for GOES 17 would look very similar. These plots assume a U.S. standard atmosphere temperature and moisture profile, as well as nadir satellite viewing angle of 0 degrees and clear skies. In this plot, note that the ozone, CO2, and 3 water vapor channels all have plots that are a bit different than the window channels. This shows the same plot without the water vapor channels, just the window channels plus ozone and CO2. Weighting functions for the majority of the infrared bands usually peak at or near the surface. The exception is the 9.6 micrometer ozone band, which has a secondary peak within the stratosphere. Note also that CO2 has a broad peak that includes much of the troposphere. These functions are calculated using a forward radiative transfer model that assumes a cloud-free sky. Weighting functions for the 3 ABI water vapor spectral bands generally have their peaks located within the middle or upper troposphere. Water vapor in the atmosphere absorbs energy at these wavelengths as it moves through the atmosphere. Absorption is most effective at 6.2 micrometers and somewhat less effective at 7.3 micrometers. Thus, a signal from farther down in the atmosphere is possible at 7.3 micrometers. The height and depth of the water vapor weighting functions are strongly influenced by two factors: the moisture profile of the atmosphere and the satellite viewing angle or zenith angle. Why is this distribution important to know for water vapor channels? It emphasizes how three-dimensional a water vapor image is. When the atmosphere is dry, the satellite views low in the atmosphere. When the atmosphere is moist, the satellite only sees high in the atmosphere. This is the 6.95 micrometer infrared water vapor image from 4Z on June 5, 2019. Over southern Baja, the 6.95 micrometer water vapor is sampling far down into the atmosphere, perhaps around 600 or 700 hectopascals, whereas over Nevada, information is coming from probably closer to 400 hectopascals. The weighting function plots are from 0Z on this day, 4 hours before the image, from El Paso, Texas, and Dodge City, Kansas. Both stations have the same total precipitable water, 0.86 inches, but a different moisture distribution in the vertical means that the weighting functions differ for the upper, middle, and low-level water vapor channels. Weighting function calculations assume clear skies. In regions with thick clouds, the water vapor information will likely come from the cloud top. Water vapor imagery does not tell you about the amount of moisture in the atmosphere. It tells you where the top of the topmost moist layer sits. In this example, considerable moisture likely exists over the Caribbean, even though the water vapor channel suggests the top of the moist layer is fairly low because the brightness temperature is warm and designated by yellow in this enhancement. In fact, this enhancement is sometimes called dry yellow. That is something of a misnomer. The total atmosphere there might not be dry, although the mid and upper troposphere certainly are. For larger satellite viewing angles, away from the subsatellite point, the water vapor weighting functions are generally shifted to higher altitudes. The plot on the right shows the 3 water vapor weighting functions for a relatively moist wintertime sounding at Fairbanks, Alaska, where the satellite viewing angle from GOES West is 73.6 degrees. The peaks are higher in the atmosphere because the path between the satellite and the station is longer, affording a greater opportunity for water vapor absorption. An identical sounding closer to the subsatellite point would have peaks lower in the troposphere. In dry sounding profiles, the water vapor weighting functions are generally shifted to lower altitudes. The plot on the right shows the water vapor weighting functions for a sounding at Hilo, Hawaii, where the middle troposphere is unusually dry due to the presence of a subtropical ridge. Note that there are secondary weighting function peaks near the 300 hectopascal pressure level. Increasing moisture aloft was absorbing and then re-emitting some of the upwelling infrared information. During the day of the Hilo, Hawaii sounding previously shown, warm thermal signatures appeared on the summits of Mauna Loa and Mauna Kea on the Big Island. The primary weighting function peaks for all three water vapor bands were located near the 600 hectopascal pressure level, which roughly corresponds to the highest altitude of those two topographic features. Because the water vapor spectral bands are infrared bands, especially in the absence of moisture, the diurnal warming and cooling of those high-altitude surface features was apparent in the GOES West imagery for bands 8, 9, and 10. Very cold temperature soundings show water vapor weighting function shifted to lower altitudes because very cold air masses are very dry. The temperature of the sounding has very little effect on the weighting function. Water vapor in the atmosphere is what is important. This figure shows three water vapor weighting functions for an Arctic air mass at International Falls, Minnesota. Some weighting function contributions are originating from the surface, for both band 9, plotted in blue, and band 10, plotted in violet. Weighting functions in very cold and dry air show that a near-surface signal can be present in water vapor bands. In this case, the thermal contrast between the cold land surrounding a relatively warm Lake Superior was present in the mid-level water vapor channel. If the air were absolutely dry, the water vapor channels would behave as window channels. Here there is enough, albeit very little, water vapor in the column that surface details are obscured. To summarize, weighting functions show the depth of the atmospheric layer, as well as the peak altitude, from which radiation being sensed by a particular infrared spectral band is originating. Weighting functions for the majority of the infrared bands usually peak at or near the surface, in clear skies, but those for the three water vapor bands can peak within the middle to upper troposphere, and are strongly influenced by two factors: the moisture profile of the atmosphere and the satellite viewing angle. The temperature of the column has a secondary effect. To explore GOES East and GOES West weighting functions for a particular radiosonde location today, visit the real-time GOES weighting function link at the bottom of the slide. There are places online where you can find more information about GOES-R and the ABI. In addition, here are some social media resources as of 2019. This concludes the module on weighting functions. Thanks for listening.